We would like to introduce to David Ramirez, which will be presenting the word safe predict, a machine learning meta algorithm that uses refusals to guarantee correctness, for who I ask a round of applause.
So we've been hearing a lot about really great projects, from mining for gold to figuring out, the quality of sleep that we're getting. We're basing the predictions that we're making in machine learning algorithms, and we're eventually, our algorithms are eventually judged based on how correct they are. What we're presenting today, or what I'm presenting today, is a meta algorithm. So we can take any of the algorithms that you're working on, we can apply safe predict on top of that, and we can achieve a target error rate that you desire. And this can be arbitrary. And what's cool about safe predict, which I'll get a little bit into it, is we're going to make no assumptions in your prediction or the data that you're seeing. So your data could be dynamic, could be static. Your algorithm could start learning and then figure something out, or it could just be already pre-trained, right? So correctness is this necessary component for algorithms. It's eventually how we're judged, how our work is judged. We can come up with an algorithm that can be pretty good at differentiating dog types, right? What I have on the left. Our algorithm sees a dog, and it predicts that it's a Labradoodle. Pretty close. But if we give it a different kind of data, right, it might be a bad prediction that it makes, right? Reliability is going to be crucial in a lot of risk-critical applications, right? Everything from medical, right? If you're using machine learning to decide if you need to take surgery or not, you want this reliability to be high, this correctness to be high. One sort of easy way to improve correctness is by introducing more experts, right? So if you're going to have a big surgery, you just don't go to one doctor, right? You ask several doctors for different opinions. Each doctor, each expert can make their opinion, their prediction, and based on those predictions, you can decide to take that surgery or not, right? If you're trying to target a specific error rate, right, something arbitrary, 95%, 99%, 99.9%, the question of how do we follow or how do we decide which expert to follow becomes pretty hard unless you make a lot of assumptions in the data that you're seeing and a lot of assumptions in the experts that you have, right? And we want to take that step back. We don't want to have any assumptions in the data that we see so that our algorithm can be applied anywhere. And we also don't want to have any assumptions, any hard assumptions, let's say, on the experts themselves. We do this by introducing what we call a dummy expert. The dummy is just simply going to be saying, let me see more data. It's essentially refusing to predict. So anytime we ask the dummy for a prediction, it's going to say, I refuse to predict, let me see more data. This is analogous to asking for more medical exams, right? So if the first few exams showed something inconclusive, you go and take another exam, right? Or if your first few digs showed a little bit of gold, but not enough, you can go in and make another dig and get another sample, right? That's what refusing to predict would be. By this introduction of this dummy, we're able to guarantee the target error rate that you're looking for. What it looks like from a sort of model systematic perspective, we have some input of data. That's that X and Z I have on the left side. No assumptions that data is just being input into your expert prediction algorithm. Your expert prediction algorithm tells us, safe predict, what prediction they made, and then we're going to decide to either follow that prediction or not follow it. Not following meaning that we follow the dummy, we refuse to predict. This is done by giving a certain weight to each expert that is being considered, and then essentially flipping coins. So it's not a deterministic who we're following. We flip coins, and based on some randomness, we follow either the expert or the dummy, right? Once these predictions are made, at some point in the future, we're assuming that we're going to be able to evaluate how good those predictions were made. It can be from 0 and 1, so prediction was good or bad, period, or it was kind of good, sort of good, like some metric evaluation between 0 and 1. And then we're going to take those what we call the loss of the prediction, and we're going to use it to update those weights that we're using to randomly pick either to follow the prediction or refuse to predict. We care about two things. We care about validity and efficiency. Validity means that we are able to meet your target error rate guarantee. And efficiency, this is not a computational efficiency, this is a prediction efficiency. So efficiency means that we are refusing a finite number of times. So if you let this run to infinity, we refuse only a finite number of times, meaning I'm not hiding behind, I refuse to predict all the time. Not as mathematically stated. We have two theorems, mathematical theorems, that show that safe predict is both valid and efficient. For validity, we do require that a predictor is good enough to meet that target error rate. We don't require to know that it exists. We don't require to know which one it is, right? We just require that it exists in the set of predictors. That's all we need. And then for efficiency, the requirements are a lot less. But there is a certain trade-off of how quickly we can find that predictor, that best predictor, and the amount of error that we're committing to. For the experimental results, I'm just going to show up here the MNIST results, but we have made use other data sets. We took data from the MNIST data set, and then for every 2,000 data points that we see, we permute the labels, right? So the first 2,000 data points, the 8 is labeled as 8. For the next 2,000, the 8 might get labeled as a 6 or a 4. So the right prediction for an 8 would be a 4 or a 6 or whatever, right? So this is to introduce sort of like a more dynamic underlying data or more dynamic randomness. And we're going to be comparing between a base predictor, doesn't matter really which one it is, a confidence-based refusal prediction algorithm, which is out in the literature. That one does use this sort of evaluation of every prediction to sort of improve if it follows or not follows. We evaluate safe predict. We can apply safe predict on top of CBR. And then we also introduce this idea of amnesic safe predict. The idea for amnesic safe predict is if we already are expecting some sort of dynamic aspect to the data, right, we can go ahead and introduce amnesic safe predict. What amnesic safe predict does is that for every fixed number of predictions, it evaluates, okay, were my predictions for the last 100, for example, were they good or were they bad? If they were good, I keep going as usual. If they were bad, I simply forget everything and I start again from 0, my safe predict algorithm. And what we can see in the top graph is the error rate. The target error rate we're trying to target was 5%. Our base predictors, you can see, is actually higher than that 5%. But the times that we predict, via safe predict in all its variations, is below that 5% error rate, right? So that's what I mean that we can meet your target error rate guarantee. Even though our base predictor itself is not good enough to meet that 5%, with safe predict, we can meet it. At what cost? At this efficiency cost, right? Efficiency, you'd want it to be higher, meaning that you're predicting more often. Efficiency goes down when you refuse more often. So you can see that that's sort of your trade-off. When we refuse to predict, it's essentially when the algorithm decides, you know, that expert might be good, but right now let's not follow it. And what we're finding is that by doing this refusal to predict, we can meet the target error rate, and we do see this decrease in the efficiency for some of the algorithms. For amnesic safe predict, that red one, you can see that it's still going up, which is essentially what we want. For efficiency, we want it to be higher. Error rate, we want it to be lower. So sort of the takeaway message from all this, what we talk about and what we've done in our work, it's available in archive, the posters here, which is also available online. We can work as a meta algorithm. So it's not exactly an algorithm itself. So whatever you're doing, we can go in and put on top safe predict and improve the target error rate. The guarantees are for the non-refused predictions. That's all something to point out. So whenever we do make a prediction, that's when our target error rate is going to be valid. There's no assumptions that we are making on the data or the prediction algorithms, right? So if you have some very unique data that you're looking at or very unique prediction algorithms, we can still work with safe predict. There's no assumptions for guarantees to hold. And what we're seeing, even if you have this dynamic environment, so if it's not just static for millions of years, the randomness, we can still apply safe predict. And there is a certain trade-off with how quickly we can follow that prediction, so how quickly we can reduce the efficiency to meet that target error rate. Thank you very much for your time.